Hello everyone, welcome to this lecture of digital electronics and circuits, and in this lecture we will be talking about a term called Boolean expressions, right? So to begin with, what is a Boolean expression? Correct? A Boolean expression is an expression which can be evaluated either to a true value or a false value. A Boolean expression may be composed of a combination of the Boolean constants which are either true or false, right? Now, in terms of most of the programming language, we have seen multiple operators like not, and, and or. Correct? If let's assume we have two variables A and B, we say A or B, which is like a bitwise or, and then A double pi B, which is like a logical or. Similarly, we have A and B bitwise or A ampersand B, which is like a logical or. And similarly, for not operation, we simply use tilde A. Correct? Eventually, depending upon the values of A and B, A or B will either be true or false. Same is the case with each and every expression which I have written over here. Correct? So the same concept applies for the digital electronics and digital circuits as well. Just as an example, right? Let's assume we have a circuit where output F is function of three inputs X, Y, and Z, and it has a value, let's assume XY plus YZ plus ZX. Correct? What would this mean? This would mean that what is the value of F when all the inputs are 0? It would be 0. How about a situation where X and Y are 1 and Z is 0? So value would be 1. Right? So we have seen a situation where F, which is an output dependent upon input, depending upon value of input, it would either be true or false. Correct? So this is a Boolean expression. And basically before going further in Boolean expression, we need to know about certain precedence terms, like we have all the arithmetic operators, right? That we have a rule of Bodmas where we say brackets are evaluated first, division is done before multiplying, and similarly addition is done before subtraction. Similarly, we need to know the order of operator precedence in terms of Boolean expressions to be able to solve multiple Boolean expressions. And Boolean expressions are important concept for digital electronics because they are used extensively for circuit minimization and understanding various laws like De Morgan law and stuff like. So let's assume we have a circuit and called F, which is equal to X plus Y Z plus ZX whole bar. We have not looked at this bar term before, but bar is nothing but it represents not. It's just like a complement, right? Z bar is equal to not of Z. Correct? Now, if we look at the multiple operators X, Y, and Z, and there are the number of precedence which we have to see over here. Now, first of all, the highest precedence goes to parentheses. So eventually, first this round brackets would be evaluated. Second precedence goes to not, next goes to and last precedence goes to or operator. So basically in the example above, first of all parenthesis would be evaluated, then this not operator would be evaluated, then we have evaluation of and operators. So y z is nothing but y into z and similarly z into x. So this would have third priority and eventually some have fourth priority, right? So this is the order of precedence. Now let's look into some of the basic Boolean expressions and their output, right? So basically we have different Boolean expression laws, right? First one is the identity law, where we say anything which is odd with 0 is the number itself, and anything which is ANDed with 1 is again the number itself. Correct? If we have to do a corollary of this, we will simply say anything which is odd with 1 has to be 1, because x could be only 0 and 1, and if we are ORing it with 1, output has to be 1. Similarly, anything ANDed with 0 has to be 0. These are the basic identity laws. Then we have something called as idempotent law. And the idempotent law says that anything which is added to itself remains the same operator having the same value. Anything which is added with itself remains the same value. Correct? Then we have something called as a complement law, where we say when we add a number to its complement, it's always 1. This is because let's assume x is 1, x bar will be 0, so 1 plus 0 will be 1, and vice versa. And the second law is anything ANDed with the complement is always 0. Correct? And the third law over here is complement of complement is equal to number itself. Then we have a next law called as commutativity law, right? Which basically says that x odd with y is same as y odd with x, and x ANDed with y is equal to same as y ANDed with x. So these are like pretty simple and straightforward rules and laws if you see, right? Identity one is basically ORing and ending with 1 or ORing and ending with 0. Idempotent law is number with itself. If you OR it, it's a number itself. If you AND it, it's again a number in itself. Complement is simply like a number OR with its complement is always 1 and with its complement is 0, and complement of complement is the original number itself. Commutativity says that order of addition does not matter and order of multiplication does not matter as well. Then we have associativity law, which says that x plus y plus z is same as x plus y plus z. Here also if we have three operators, order of addition does not matter. Same is true with multiplication. X by z is same as xy into z. Then we have a law of distributivity. It simply says if I have a operator x into y plus z, right? This would be same as x ANDed with y or with x and y, right? So basically, if you see, we got a parenthesis got precedence over here. So parenthesis got precedence. So x into y, x and y plus x and z. Okay, and similarly, the other law would be for multiplication, where we say x plus yz would be same as x plus y into x plus z, right? And how does this come? X into x is nothing but the number itself, xz plus xy plus yz, right? X into 1 plus z is x plus y into x plus z. So which is nothing but if you take x common over here, 1 plus y is 1. So x plus yz. This is a distributivity law. Next law is something which we call as absorption law. And this is equal to, this says that x plus xy, which we have used above already. Basically this could be rewritten as x into 1 plus y. 1, any number odd with 1 is 1 itself. This would be equal to x. Similarly, x into x plus y would be equal to x into x plus x and it with y. X into 1 plus y. X into x is x, x plus 1 plus y, 1 plus y is 1. This would be x. Correct? Now we have next set of a law which is called simplification law. And in this law, we have something called as x plus x bar y is same as x plus y. This is because what we can do is x into, so basically if x is 0, right, if x is 1, x bar will be 0, so answer would be x, remaining would be x. And similarly if x is 1, x is 0, this would be 0, and x is 1, output would be 1, and x is 0, output would again be x dependent upon what is the value of y. This is the simplification law. Next law is one of the most important laws in digital electronic circuits, and that is called as De Morgan's law. And the De Morgan's law says that x plus y whole complement is equal to x complement into y complement, and additionally it says xy complement is equal to x complement or with y complement. This is the most important law of digital electronic circuit. You will see this is used extensively in lot of XOR gates and XNOR gates. This is very important. X plus y whole bar is equal to x bar dot y bar. Xy bar is equal to x bar plus y bar. Correct? Now we have learned some of the laws over here. If you see, we have looked into identity law, idempotent, complement, commutativity, associativity, distributivity, absorption law, simplification, and De Morgan's law. Let's use these laws to simplify some of the Boolean expressions. Let's assume I have an expression, say f is equal to xy plus xy bar plus xz. Can we simplify this circuit? So this will be simplified as x into y plus y bar plus xz, y plus y bar. Number odd these complements is always 1. So this will become x plus xz. Again, if we take x as common, this will be 1 plus z. A numbered odd with 1 is 1. So this is like x into 1, which is like x. So basically, if you see this output, which is function of x, y, and z, is actually could be represented as f of x is equal to x. This is dependent only on x. Y and z are don't care over here. Correct? So this is one example of circuit simplification. Let's look at one more example. Let's say we have a circuit called f is equal to x plus x bar y plus x bar y bar z plus x bar y bar z bar alpha plus x bar y bar z bar alpha bar beta. Correct? Can we simplify this circuit? Yes, we can. What we can do over here is we can say x plus, let's take x bar common, y plus y bar z plus y bar z bar alpha plus y bar z bar alpha bar beta. Similarly, what we can say is x plus, and so basically, do you remember the simplification law which we studied over here? X plus x bar y is nothing but x plus y. So basically, this would turn out to be something like x plus y plus y bar z plus y bar z bar alpha plus y bar z bar alpha bar beta. Now what we can do is we can do x plus y, we can take y bar common, z bar alpha plus z bar alpha bar beta. Again simplification law, x, this is in this case this will become our one term x, this is another term y, this is another term x. So basically this is okay, so sorry, so this is like x plus x bar y, so this would be equal to x plus y, so this will come out to be x plus y plus this term z plus z alpha plus alpha bar beta. Similarly what we can do is z plus, we can take z bar common, alpha plus alpha bar beta, so this will again become one term x plus x bar b, so x plus b, z plus alpha bar beta, which is nothing but x plus y plus z plus alpha plus beta. So basically this expression f is basically OR of all the inputs x, y, z, alpha and beta, and we don't need to implement a complex circuit with all these AND gates and set of inputs. Okay. So basically with the help of Boolean expression we were able to minimize this circuit and simplify it. Okay, and now you remember that we looked at a De Morgan's law where we said x plus y whole bar is equal to x bar dot y bar, and x by bar is equal to x bar plus y bar. So basically this is like bar is nothing, as we discussed in the beginning, right? Bar is nothing but complement. Now if we have a function say f which is equal to a bar b c bar plus a bar B bar C. Now if I ask you to find complement of this function, f complement is equal to f bar, which is nothing but a bar b c bar plus a bar b bar c complement. So basically this becomes x, this becomes y. So the output would be as per De Morgan's law x bar dot y bar. So basically this would become a bar b c bar whole bar dot a bar b bar c whole bar. And then again it is like x y z bar. So this will become x bar plus y bar plus z bar eventually, right? So what we would say is this implies a plus b bar plus c into a plus b plus c bar. This will be the complement function of the above function, right? Is this clear or not? Okay, this is a complement. F complement is f bar and we use a De Morgan's law to evaluate it. So f complement for this function is this particular function, right? Is this fine? Okay, great. Now switching gears, we would look at one more example, right? Let's assume we have a function called f is equal to, so basically f complement in this case would be nothing but f bar, which is equal to x y bar plus x bar y for complement. This would be equal to x y bar complement dot x bar y complement. So this would be equal to x bar plus y bar x bar bar plus y bar. It's nothing but x bar plus y into x plus y bar. This is a complement. So I hope this lecture was useful and you were able to look at, understand and evaluate and understand basic functionality of different Boolean expressions and various Boolean precedence order of various Boolean operators and various Boolean expression laws. Thank you.